Everyone, and welcome to our today's class. It is our first lesson on the first topic of Form 2 work, which is magnetism. So as usual, let me start by giving you the quote of the day, which states that it costs nothing to say I'm sorry, comma, excuse me, comma, thank you, and please help me. It costs nothing to say I'm sorry, excuse me, thank you, and please help me. So we'll discuss that quote at the end of our class today. So let's look at magnetism. So where is the word magnetism originating from? So magnetism is simply from the word a magnet. So let's look at the discovery of a magnet. So a magnet was discovered from a given material called lodestone, or sometimes we call it the magnetite. So lodestone was first discovered by a Greek shepherd called Magnes, who was attending to his sheep in a region of northern Greece called Magnesia. That is, Magnesia is Magnesia. So this shepherd, actually, he discovered a naturally occurring material called lodestone, or what we are calling magnetite, which was a form of iron ore that attracts some materials when brought near it. So lodestone was observed to settle facing the north-south direction, that is when freely suspended. So this property of lodestone has been used to make what we call the present magnets, what we call the present magnets. So from the discovery of lodestone or the magnets, various scientists actually came up. For example, we have Hans Christian Ørsted in the year 1819 discovered that electric current can influence compass needles. Also, we had discoveries such as that of Michael Faraday in the year 1831, who discovered that motion of magnet towards or away from a given circuit could actually produce current. So Faraday, about the Faraday's law, we'll look at it in a given topic in Form 4. So today we are looking at magnetism. So we have said that magnetism is from the word a magnet, and you can see that the word a magnet is coming from a lodestone, which was also called a magnetite. Remember, it was also discovered in Greece, in northern Greece, at a place called Magnesia. So from the word Magnesia, we obtained the word a magnet. Also, the person who discovered it was a shepherd who was called Magnes. So Magnes, actually, we derived the word a magnet. So at magnetism, the first thing we look at is the properties of a magnet. That is, what makes up a magnet. So a magnet has two properties. One is what we call magnetic poles, or what we call the polarity, and also the second property of a magnet is what we call the directional property. So if you are asked to give any two properties of a magnet, you just say one is magnetic poles and two is directional property, or you can just say one is polarity and two is directional property. So let's start by looking at the magnetic poles as a property of a magnet. So when a bar magnet is dipped into iron filings, the iron filings cling mainly around the ends of the bar magnet. So here is my bar magnet, which is dipped in iron filings. So you just take a bar magnet, then you throw it, or you dip it in many iron filings. So if a bar magnet is dipped in iron filings, the iron filings are observed to cling. To cling is to attach themselves. They are observed to cling mainly around the ends of the bar magnet. So you can see many iron filings are at the ends of the bar magnet. So we have many iron filings here, many here. We also have many iron filings at the end of a bar magnet, but at the middle of the bar magnet there are only very few iron filings. So what does this show? So we are saying that when a bar magnet is dipped into iron filings, the iron filings cling mainly around the ends of the bar magnet. So this shows that magnetic attraction is strongest at the ends of the bar magnet. So this ascertains or proves that magnetic attraction is strongest at the ends of the bar magnet. So the ends of the bar magnet where the power of attraction is greatest is called the poles of a magnet, or simply magnetic poles. So these ends of the bar magnet where the force of attraction or the magnetic power is strongest, these are what we are calling the poles of a magnet. The poles of a magnet, or simply magnetic pole. So that is the first magnetic property. That is the magnetic poles. That is the first property of a magnet. So we have just said that when a bar magnet is dipped into ion filings, the ion filings clink mainly around the ends of the bar magnet, and this shows that magnetic attraction is strongest at the ends of the bar magnet. So the ends of the bar magnet where the power of attraction is greatest are called the poles of a magnet, or simply magnetic poles. So someone can ask you to describe a simple experiment to show the polarity of a magnet. You can be asked to describe a simple experiment showing that the poles of a magnet are at its end. So if you are asked such a question, you just say that you dip a bar magnet in ion filings, then you just observe where most of the ion filings will clink. So it is observed that most of the ion filings cling at the ends of the bar magnet, showing that the force of attraction are strongest at the ends of the bar magnet. Then you say that the ends of the bar magnet where the force of attraction is strongest, those are what we call the poles of a magnet. Then the second property of a magnet is what we call the directional property, or the direction. So when a bar magnet is freely suspended, that is, to suspend is just to tie a bar magnet as shown here and hang it in free air. For example, you can hang it on a tree or on any other relevant hanging instrument. For example, in a laboratory you could use what we call sometimes we use a stand. You just hang it freely in air such that it is suspended. So the directional property here, when a magnet is freely suspended in an open place, it will rest along a certain particular direction. So it aligns along the north-south direction as shown here. So if a bar magnet is suspended freely in air, it is observed that it aligns in a specific certain direction. So it aligns in the north-south direction, such that this is the northern side and that is the southern side. So it aligns in the north-south direction. Now we are saying that the poles which points towards the north, that is, you can use maybe a compass direction to know which side is the north direction and which side is the southern direction. So the pole of the magnet which points towards the north direction is called the north-seeking pole. Is called the north-seeking pole, or simply the north pole. So if a bar magnet is actually suspended in free air in open place, it rests along a certain particular direction. That is, it aligns in the north-south direction. Then we are saying that the pole which points towards the north, that is this particular pole of the magnet which points towards the northern direction. Remember, this is our magnetic axis. So it aligns along the magnetic axis. So the pole or the side of the magnet which aligns along the northern direction, that pole we call it the north-seeking pole, or simply the north pole. So this is our north pole because it is aligning along the magnetic axis but towards the northern direction. Whereas the pole which points, that is this pole here, whereas the pole which points towards the southern direction is called the south-seeking pole, or simply the south pole. So this is what we are calling our south pole because it points in the southern direction. That is when a bar magnet is freely suspended in air. Therefore, a magnet can therefore be used as a compass direction. A magnet can be used by a compass because it can be used to show you which side is the north pole and which side is the southern direction. So the pole which points towards the northern direction is called the north-seeking pole, or simply the north pole, which we denoted by capital N, and the pole which points towards the southern direction is called the south-seeking pole, or simply the south pole. So south-seeking because the south pole, because it is seeking or it is aligning towards the southern direction. The north-seeking pole because it is seeking towards the north pole. That is, it is aligning towards the north direction of the magnetic axis of the Earth. So you can be asked to describe an experiment to show magnetic poles, or you can also be asked to describe an experiment to show the directional property of a magnet. So you just suspend a magnet freely in air, then you observe the alignment of the magnet. So if it aligns in a specific direction, then that proves that that is a magnet. But if it aligns in any other direction, that is maybe not in the north-south direction, then that shows that that particular material is not a magnetic material. So 2, we look at magnetic and non-magnetic material. Now, what are magnetic materials and what are non-magnetic material? So there are certain materials which, when brought closer to a magnet, so this is just an experiment to prove which materials are magnetic and which materials are non-magnetic. So if you're asked to describe a simple experiment to differentiate between a magnetic and non-magnetic material, you just suspend a rod or any other material, you hang it in air freely, then you bring a magnet, you bring one pole of a magnet towards that material, then observe what happens. If the material is attracted towards any pole of a magnet, then that material is called a magnetic material. However, if a material is observed not to be attracted to any pole of a magnet, then such a material, we call it non-magnetic material. So in short, what is a magnetic material? So a magnetic material, these are magnetic materials, are those materials that are attracted by a magnet. So a material that is attracted by a magnet, we call it a magnetic material. So materials that are attracted by a magnet is called a magnetic material. Whereas materials that are not attracted by a magnet, we call them non-magnetic materials. So materials that are attracted by a magnet are called magnetic materials, whereas materials that are not attracted by a magnet are called non-magnetic material. Remember, non means opposite. So if a material is attracted to a magnet, we call it a magnetic material, and the opposite of that, that is non-magnetic. Those are materials that are not attracted to a magnet. Now we can also give examples of magnetic and non-magnetic material. So most metals, for example iron, they are called magnetic materials. Why? Because they are easily attracted to a magnet. So if you are asked to give examples of magnetic materials, you just say we have iron, we have nickel, we have cobalt. Those are magnetic material. So any material that is attracted to a magnet or that is attracted by a magnet is called a magnetic material. So example, we are talking of iron, we have nickel, we have cobalt, we can have aluminium, and most metallic materials are actually magnetic material. Whereas materials that are not attracted to a magnet, we call them non-magnetic material. Examples of non-magnetic materials are, 1 is most plastic materials, 2 we have wood, plastic, wood, and even rubber. Those are examples of non-magnetic materials. Then under magnetic materials, we have the types of magnetic materials. So we have different types of magnetic materials. 1, we have magnetic materials called ferromagnetic material. Remember, the word ferro is coming from remember iron in chemistry is denoted by Fe, that is Fe. So that is where the ferro is coming from. So ferro has to do with iron. So ferromagnetic materials, we also have other materials called paramagnetic materials, and we also have other materials called diamagnetic materials. Now what are ferromagnetic materials? So ferromagnetic materials, these are magnetic materials that are strongly attracted by a magnet. That means we have certain materials which can be weakly attracted by a magnet and others will be strongly attracted by a magnet. So materials that are strongly attracted by a magnet, we call them ferromagnetic materials. So ferromagnetic materials, these are materials that are strongly attracted by a magnet. Examples of ferromagnetic materials include iron, nickel, and cobalt. Iron, nickel, and cobalt. So if you are asked to define what are ferromagnetic materials, you just say that these are magnetic materials that are strongly attracted by a magnet. Example is iron, nickel, and cobalt. Then paramagnetic materials, this is the opposite of ferromagnetic materials. So paramagnetic materials, these are magnetic materials that are weakly attracted by a magnet. That is, their force of attraction to a magnet is actually very small or weak. So we are saying that paramagnetic materials, these are magnetic materials that are weakly attracted by a magnet. Magnetic materials that are weakly attracted by a magnet, we call them paramagnetic materials. Examples of paramagnetic materials is aluminium. For example, you can just try a simple experiment at home. You take a nail, you take an iron nail, and also you take a cooking pan made of aluminium. Then try bringing those two particular materials close to a magnet. You will realize that the extent or the force by which an iron nail will be attracted by a magnet will be different from the force by which a material called, that is aluminium, cooking pan will be attracted to a magnet. So you realize that a nail will be strongly attracted to a magnet. That is, an iron nail will be strongly attracted to a magnet, whereas aluminium cooking pan will be weakly attracted to a magnet. So materials that are strongly attracted to a magnet are called ferromagnetic materials, whereas materials that are weakly attracted to or by a magnet are called paramagnetic materials. So an example we have given aluminium. Now we have other materials which we call diamagnetic materials. Now what are diamagnetic materials? So diamagnetic materials, these are materials that are repelled by a magnet. These are materials that are repelled by a magnet. So when these materials are brought close to a magnet, instead of being attracted, they will be repelled away. So materials that are repelled away by a magnet, we call them diamagnetic materials. Now only like poles of a magnet are actually diamagnetic. So when we talk of like poles, we mean a north pole with a north pole. So a north pole with a north pole, they will always repel each other, whereas a south pole and also a south pole will also repel each other. So materials that are repelled by a magnet are called diamagnetic materials. So example is just a north pole with a north pole. Another example is a south pole with a south pole. So those ones, we call them diamagnetic materials. Then what we call the basic law of magnetism. We look at the basic law of magnetism. So you need to know how to state the basic law of magnetism. Remember, this law has a closer relationship with the law of electrostatic charges, only that in that case you are dealing with electric charges or current, but in this case you are dealing with the magnets, magnetic forces, or what we call the magnetic field. So how does the basic law of magnetism state? So the basic law of magnetism states that like poles repel and like poles attract. Like poles repel, and like poles attract. So if you are asked to state the basic law of magnetism, you simply say that the basic law of magnetism states that like poles repel, and like poles attract. Like poles repel, and like poles attract. Now what do we mean by like poles? Like poles, when we say something is alike, we mean they are similar or they have some properties, some common properties. So when we talk of like poles, we have just said that we have a magnet has two poles. That is when we are looking at the polarity property of a magnet. We said we have what we call the north pole or the north seeking pole, and we also have what we call the south pole or the south seeking pole. Now the north pole is represented by capital N, then a south pole is represented by capital S. So like poles, we mean when a north pole with a north pole are together, we call them like poles. Also when we have a south pole with a south pole, we call them like poles, because they are both north with north and also south with south. However, when poles are different, for example, a north pole with a south pole, those ones we call them unlike poles. So the surest test for polarity is repulsion. Why? Because since repulsion, so the surest test for polarity is repulsion, since attraction can occur between any poles of a magnet and a magnetic material, while repulsion can only occur between like poles of a magnet. So there is usually a question that is asked that you state why repulsion is the surest test for polarity while attraction is not taken as the surest test for polarity. So we've said that like poles means a north pole with a north pole or a south pole with a south pole. But unlike poles means a north pole with a south pole, then a south pole with a north pole. So this is an experiment demonstrating the basic law of magnetism. So if you just take, you suspend a magnet or you just tie it freely, then leave it to hang in air. Then you bring a free magnet with the north pole close to the north pole of the other magnet. Then observe what happens. So if a north pole is brought close to the north pole of the other magnet, they are observed to repel each other. That is, when you bring this north pole close to this north pole of the magnet, this magnet will move away or it is repelled, actually proving the basic law of magnetism. So two like poles will always repel each other. So if a north pole is brought close to a north pole, they repel each other. However, if you take this end, if you take a south pole, then you bring it close to a north pole, they will attract each other. They will attract each other. Also, if you take a south pole, you take it close to a south pole, they repel each other. But if you take a north pole close to a south pole, they will always attract each other. So the basic law of magnetism states that like poles repel, comma, and like poles attract. Then we are saying that the surest test for polarity is repulsion, since attraction can occur between any poles of a magnet and a magnetic material, while repulsion can only occur between like poles of a magnet. So we are saying that the only sure way of testing the poles of a magnet is through repulsion. Why? Because repulsion can only take place between two like poles. That is, if you bring a north pole close to a north pole, they will always repel each other. So in this case, we assume we have one magnet whose polarity is known, then we have another magnet whose polarity is not known, but we want to use the first magnet to identify the polarities of our second magnet. So if you have another magnet whose polarity is not known, then you bring that magnet close to a north pole. If they attract each other, if they appear to repel each other, then you will know that the pole that you actually brought close to this north pole of a magnet was surely a north pole. Why? Because repulsion will only take place between two like poles. Also, if you bring a certain end of a magnet whose polarity is not known close to a south pole, then you realize that they are attracting each other. It means the poles are opposite. That is, but if you bring any pole of a magnet close to the south pole of a magnet, then you realize that they are repelling each other. Then it means surely the pole that was on that magnet is a south pole. Why? Because like poles will always attract each other. But suppose you are using attraction to test for polarity. Remember, attraction can take place between any any pole of a magnet and actually a magnetic material. So if you bring a material that is not known whether it is a magnet or not, for example, if you bring an iron rod close to a south pole of a magnet, it will be attracted. You also bring another magnetic material, the same iron rod close to a north pole, it will still be attracted. So you will not know whether the material that you have brought close to a magnet, whether it is a magnet or a magnetic material. So attraction is not regarded as the surest test for polarity, because attraction can take place between any pole of a magnet and a magnetic material. But repulsion is the only surest test for polarity. Why? Because repulsion can only take place between two like poles of a magnet. Why? Because repulsion can only take place between like poles of a magnet. So there is a question that usually asks that you state the surest test for polarity, or you can be asked to give a reason why repulsion is the surest test for polarity. So the reason is because repulsion can only take place between like poles of a magnet. So we are saying that the surest test for polarity is repulsion, since attraction can occur between any pole of a magnet and a magnetic material, while repulsion only occurs between like poles of a magnet. That question is very common. That's why I'm insisting on it. So the reason why attraction is not the surest test for polarity is because attraction can occur between any pole of a magnet and a magnetic material. Then the reason why repulsion is the only surest test for polarity is because repulsion only occurs between like poles of a magnet. Then so we've discussed about the test for polarity. Then we have said that basic law of magnetism states that like poles repel while unlike poles attract each other. Next we look at magnetic field patterns, the magnetic field pattern. Now what is a magnetic field? So a magnetic field is a region around a magnet where the forces of attraction or repulsion are strongly felt. A magnetic field is a region around a magnet where the force of attraction or repulsion is strongly felt. So this is what we mean. For example, if this is our bar magnet with a north pole here and a south pole here, then we have a certain region around that particular magnet where when you bring a magnetic material, it will be attracted. But when you bring a like pole, that is another magnet of similar poles, they will be repelled. So if you take, for example, a nail closer to a magnet, you bring a nail like somewhere here, it will not be attracted. But you bring it closer to a magnet, it will always be attracted. So we have a certain region within which a nail or any other magnetic material, when placed closer to that particular magnet, it will either be attracted or if they are like poles, they will always repel each other. But if you take a magnetic material or a magnet far away from another magnet, there will be no attraction or repulsion. So that region or the area around a magnet where the forces of attraction of the magnet are felt, that region is what we call a magnetic field. So we are saying that a magnetic field is a region around a magnet where the force of attraction or repulsion is strongly felt. A region around a magnet where the force of attraction or repulsion is strongly felt. Then two, we look at the direction of magnetic field. The direction of magnetic field. Now where do magnetic field move from or towards? So the direction of magnetic field at a point is the direction in which a freely suspended north pole would move if placed in that particular field. So we are saying that the direction of a magnetic field at a particular point is the direction in which a freely suspended north pole would move in if placed in that particular field. So remember, if you place a magnet in a magnetic field, it aligns towards the north-south direction. So we are saying that the direction of that particular magnetic field, that is where the field is moving from and towards, at a particular point is the direction in which a freely suspended north pole would move if placed in that particular field. Then we look at what we call so here is experiments actually showing different magnetic field and how they can actually take place. But before that, let's look at magnetic field lines. So a magnetic field line is just the path along which magnetic forces pass. A path along which magnetic force pass. For example, here a magnetic field line can be located by use of two methods. One is by use of a plotting compass, and two by use of what? Iron filings, by use of iron filings. So here in these two methods, one is that you just bring your magnet here, then we have your plotting compass. So magnetic field mapped by a plotting compass. So if magnetic field are mapped using a plotting compass, it has an advantage. Why? Because the magnetic compass shows you the direction of the field. Remember, the magnetic field will always move from the north pole towards the south pole, just like in charges, where we said that current will always flow from the positive terminal towards the negative terminal. So the positive terminal in this case represents the north pole, and the negative terminal in this case represents the south pole. So the advantage of using a plotting compass to locate magnetic field is that it indicates the direction. It shows you both the pattern and the direction. So, but if you use iron filings, that is, you just take maybe a paper, then place on it some iron filings, then place a magnet beneath or under that paper. You will just see the distribution of the iron filings. This will be the distribution of the iron filings. So the path taken by the iron filings represents the magnetic field lines. So you will realize that most of the iron filings, of course, will cling or attach themselves at the poles. Then the others will be moving in a circular path, that is in this manner. So this path represents what we call the magnetic field lines. So we are saying that iron filings only show the pattern. That is, this is what we are calling the pattern, the movement of the iron filings. That is what we are calling the magnetic field. So magnetic field, we said, is just the region around a magnet where the force of attraction or repulsion are strongly felt. So the iron filings will move up to certain region here, but the region far away from the iron filings, they will not be attracted, meaning that that region is not within the magnetic field, because the magnetic field is just a region around a bar magnet where the force of attraction or repulsion are strongly felt. So if you use this should be using actually the iron filings. I think it was an error. So this is the pattern using iron filings. So if you use iron filings to plot the magnetic field or the magnetic field lines, the iron filings only show you the pattern, but they do not show you the direction. That is, there is no arrow showing that the fields are moving from maybe the north pole towards the south pole. But if you use a plotting compass, it will always show you the direction. So iron filings only show the pattern, that is the movement, the pattern of the field, but a plotting compass shows both the pattern, that is where the fields are moving from and towards, and also the direction of the magnetic field. So this arrow actually shows that the fields are moving from the north pole towards the south pole. So if someone asks you to give the advantage of using a plotting compass over using iron filings to plot the magnetic field or the field pattern, you just say that a plotting compass shows both the pattern, that is the magnetic pattern, and the direction, whereas iron filings only show the pattern but do not show the direction of the magnetic fields. Then we look at various types of magnetic fields. So we have two types of magnetic field. One, we have what we call uniform magnetic field, uniform field strength, and what we call the varying magnetic fields. So uniform simply means that the fields are uniform or they are parallel to each other, as shown in this particular arrows here. So this shows that the fields are moving from this direction towards that direction. But if the fields are varying, it means at some certain point the fields are stronger, at some certain points the fields are actually weaker. So like for this case, in this particular point Y, where the fields are far away from each other, we say that the magnetic field in this case is weak. But if the fields are closer to each other, like the magnetic field lines are showing here, it means at point X the magnetic field is actually strong, but at point Y the magnetic field is weaker, because the magnetic field lines are far away from each other, or they are diverging from each other. But for a uniform magnetic field, here the magnetic field strength is uniform or is the same at any particular point within that magnetic field. That is, the magnetic field at this point is the same as the magnetic field at the midpoint here, is also the same as the magnetic field at the other end. But for varying or non-uniform magnetic field here, at one point the magnetic field is strong, that is at point X. At the other point the magnetic field is weak. Why? Because the magnetic field lines are actually moving away from each other. Now, what are these that we are calling magnetic field lines? So let's define what we mean by magnetic field lines. So magnetic field line is just the path along which magnetic force passes, the path along which magnetic force passes. Like for this case, we have magnetic force is passing from here towards this path up to that. For this case, the magnetic forces are passing downward through this path. They are also passing through this path. They are also passing through this downwards path, and they are also passing through this upper path. So just the path along which magnetic force passes, that is what we call magnetic field lines. So magnetic field lines is just the path along which magnetic force passes. Then we look at they have certain properties. So let's look at the properties of magnetic field lines. That is, what are their characteristics. So one of the properties of magnetic field line is that they originate from the North Pole and end at the South Pole. That is as shown here. So magnetic field lines originate, or they start from the North Pole and end at the South Pole. So that is the first property of magnetic field lines. They originate from the North Pole and end at the South Pole. So if you have to show direction or arrow, the arrow should be pointing towards the South Pole. That is originating from the North Pole towards the South Pole. The second property of magnetic field line is that they repel each other sideways and form closed paths, never intersecting other lines of force. That is like as shown here, you will not see one line of force cutting through or intersecting another line of force. So they move parallel to each other and they never intersect each other. So why? Because they always repel each other. Remember, they have been originated from the same pole. So if they are coming from here, they are actually North Pole, they have the same poles. So a North Pole and a North Pole, they always repel each other. So magnetic field lines always repel each other. So we are saying that the second property of magnetic field line is that they repel each other sideways and form closed paths, never intersecting other lines of force. That is, they form closed path. From the North Pole, they close at the South Pole. From the North Pole, this one also close at the South Pole. From the North Pole, they also close at the South Pole. So they repel each other sideways and form closed path, never intersecting other lines of force. Then the third and the last property of magnetic field lines is that the closer they are closer together where the field is strongest. Yeah, that's like here. At point X, the magnetic field lines are very close to each other. So we said that this point, this is where the field is actually strongest. This is where the magnetic field is strongest. At point Y, the magnetic field lines are far away from each other, meaning the magnetic force or the magnetic field is weakest at point Y and strongest at point X. So magnetic field lines are closer together where the field is strongest. They are closer together where the field is strongest. So in short, we have said that the three properties of magnetic field line is that one is that they originate from the North Pole and end at the South Pole. Two, they repel each other sideways and form closed paths, never intersecting other lines of force. And then three, they are closer together where the field is strongest. They are closer together where the field is actually strongest. So we've come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day stated that it costs nothing to say I'm sorry, excuse me, thank you, and please help me. So what does this particular quote mean? So it is our belief in life that when someone says I'm sorry, excuse me, thank you, or please help me, then it means that they are weak. But that is not true. You cannot say that when someone is saying I'm sorry, excuse me, thank you, and please help me, that is weakness. That is not a weakness. In fact, asking for help when you don't know something isn't a sign of weakness. In fact, it is a sign of strength. Because when you ask for help when you don't know something, it means it is a sign of strength, because it shows that you are willing to learn. So make it a habit to often use the phrases I'm sorry, excuse me, thank you, and please help me in your conversations. Why? Because these particular phrases, they may appear to be simple and obvious phrases, but believe me, they can make a huge difference in someone's life. And lastly, remember this, that the ability to learn is a skill. Remember this, ability to learn is a skill that can actually be learned. But the capacity to learn is also a skill, but the willingness to learn is a choice. That is, if someone is willing to learn, that is a skill that can be learned. But the capacity for someone to learn is a gift that you acquire. But the willingness for someone to learn, that is your own choice. So we have said that the ability to learn is a skill. The capacity to learn is a gift. But the willingness to learn is a choice. This is Kind Tuition Academy. Kindly hit that subscription button on YouTube. Thank you.